Hello and welcome to our session for physical sciences. My name is Temba. Today we are focusing our attention on resistors in parallel. We want to explore exactly what happens, if you have a circuit whereby you keep on adding resistors in parallel, how exactly that affects, the magnitude of current, how it affects the potential difference, terminal potential difference, and a host of quantities in as far as a parallel circuit is concerned. Now let's locate parallel resistors within the broader, section of electrical circuits. Right. So from our, concept map, we understand that by now, in the context of circuits, right? In the context of circuits, we are saying that, you have got two types of connections. We've got a series circuit, which by now you may recall that it has a lot to do with potential dividers while current remains constant, and exactly what effect does that have if we add more resistors on the current as well as the voltage as well as resistance. But today our focus will be on the parallel circuit. We would want to investigate how that affects the magnitude of current and voltage as well as resistance if we keep on adding resistors in parallel. Right. Now, the thinking that's going to maybe guide our discussion for this session is that think about what exactly happens to the magnitude of current. Okay, we are worried about current in a circuit when more resistors are connected in parallel. All right. Remember, if we talk of a parallel circuit, it's in the context of saying that we've got more than one path for charge to actually flow. So current has got more than one options or alternatives to follow in a complete circuit. That's what parallel means. Okay. Now we want to see how adding parallel resistors in a parallel circuit actually affects the magnitude of current as well as potential difference across each resistor. But for the resistors in this discussion, we would use light bulbs because we know a light bulb is a typical example of a resistor. What makes us say that? We would remember that a resistor is any electrical device or component that actually transforms electrical energy to other forms. So what does a light bulb actually do in a circuit? Much as a circuit is about energy transformation or energy change, what happens when electrical energy reaches a light bulb? The light bulb serves the role of converting that electrical energy into light, and maybe some of it to heat, right? So we would obviously think of a light bulb as an example of a resistor, right? So the second thought is, what happens to the terminal potential difference? That's the voltage, all right? Which is, the voltage, right? What happens to the voltage when more resistors are connected in parallel? So it is essentially about the parallel resistors, right? Okay, these are the keywords, okay? And we've already noticed that, when it comes to definitions, it's a all or nothing kind of a situation. It's either you remember the definitions or you don't. So remember again, once more, that the examination guideline serves as our point of reference in as far as the wording keywords that must be used in the correct context is concerned. So as a result, always refer to the exam guidelines for what is acceptable in terms of definitions. Knowing the keywords is not enough. Beyond that, you need to correctly use those keywords in the correct context. So it's either you get 2 marks for defining or you get naught or 0, right? So it says here, resistor, which is a device. Okay, a resistor is a device, okay, in a circuit. It could be a light bulb, for example, okay? So a light bulb would serve as a perfect example of a resistor for the purpose of today's discussion. And then resistance is the quantity, okay? Now, let's try and remember that when we talk about resistance, we're talking about a quantity, while a resistor is a device that offers resistance in a circuit. And resistance has to do with the opposition of flow of charge or opposition to current in a complete circuit, okay? So a quantity, the quantity concerned is resistance, while a resistor, it's a component or a device that will offer a resistance in a circuit, right? So we also remember that equivalent resistance has to do with total resistance. We spoke about this, about, you know, equivalent. Sometimes it could be effective resistance. So the word equivalent and effective could be used interchangeably to refer to one and the same thing. Another word or term that we'll use a lot in our discussion is current dividers in the context of parallel circuits. Right. Now, we know that resistance is the opposition to the flow of charge. So that's the definition of resistance, okay, as a quantity. So we also know that different components, these are electrical components, that is, they provide varying resistance in a circuit, okay? So an electrical component that has a high magnitude of resistance, okay, will require more energy transfer. Okay, what do we mean by that? Remember, in real life, you know, beyond the theory, we know that we have got many circuits in our everyday life. You know, if you think about the resistance that a light bulb, offers compared to the resistance that a heater, which is another appliance or a device that we have in our homes. You know, a heater has got greater resistance. Why? Because the amount of work that a heater does in terms of transforming electrical energy to heat is comparatively greater than that of the light bulb converting electrical energy into light, okay? So that's what we mean when we say different electrical components or devices, appliances, they offer varying, you know, magnitudes of resistance. This is what happens in real life, right? Okay, so an electrical resistance is also measured in ohms. So ohm is the SI unit, okay? R is the symbol for the quantity, okay? While omega, which is a Greek letter from the Greek alphabet, represents ohm, okay? So when do we have an ohm of electrical resistance? Let's remind ourselves once again. 1 ohm of electrical resistance is actually equals to 1 volt per ampere of current, okay? So 1 ohm of electrical resistance allows an ampere of current, which is 1 ampere, all right, to pass through, a resistor, through which the potential difference is 1 volt that's applied across it. So it takes us back to that mathematical, you know, equation, right? Okay, so resistance, conductors also, in most cases we choose to ignore the resistance that conducting wires offer in a circuit. Hence, we'll say the conducting wires have negligible resistance. Okay, so this term, negligible resistance, is very common in, in our discussion of circuits, because it tells us that, we may ignore the leakage resistance that conducting wires, the ammeter, offers in a circuit. So if they say the battery has negligible resistance, it means that the source does not offer any resistance to the flow of charge. It means all the current passes through the battery. So this is negligible, okay? Okay, negligible, right? Okay, resistance, okay. So this says to us that the amount of resistance is very low for us to actually ignore it, okay? So how do we calculate resistance? It takes us back, resistance is the ratio of voltage and current in a circuit. It could be the total resistance. If we're talking about the resistance of the entire circuit, we know that the total resistance is equal to the terminal potential difference, which is the total voltage in the circuit, divided by the total current. So this is the total current that goes through the battery versus the voltage of the battery when there is current in the circuit, which is our terminal potential difference. So the notation will vary. Suppose we want to determine total resistance or resistance through a resistor R1. So we'll say R1 is equal to potential difference across R1 divided by the current that goes through R1. So it's just the notation there that you need to take note of, okay? So to measure total resistance, we need to measure the terminal potential difference. So this is what we are talking about, okay? And the total current through the battery, okay? Right, so how do we construct a simple parallel circuit? Okay, what is it that we need? We need a battery, which is the energy source, or a cell, whatever the case may be. We need a conducting material, in terms of physical properties, these are materials that allow charge to flow through them, okay? A resistor, which could be, in this case, we can use a light bulb, it's still fine, okay? Because it's a perfect example of a resistor in a circuit. We need an ammeter for measuring current, okay? To know how much charge passes through a point per second. We need a switch to complete or break the circuit, and then we also need a voltmeter, okay, to measure potential difference across a component. So in ammeter, you remember this is the symbol, while the voltmeter is that, okay? Right, so we're going to set up, you know, a circuit, a simple circuit like the one that you see. And then the question is, how do resistors in parallel affect the flow of charge in a simple circuit? So let's go to our simulation, right? So if we go to our simulation, this is what we have, okay? Now, I'll open that switch for now. You'd realize that there's zero current in this circuit, or there are no charges that are flowing. Why? Because we'll use the conventional current. Why? Because the circuit is broken, okay? But what if we complete the circuit, okay? What if we complete the circuit? There will be current in the circuit, okay? So if we complete, there is our conventional current flowing from the positive terminal to the negative terminal. The reason why there is no current in the other light bulb is because that part of the circuit is broken. So it's not complete because the switch is actually open. Now, what does that 0.9 ampere of current mean? It means that when the first switch is closed, the amount of charge that passes through any point, even through the light bulb, is actually 0.9. It means 0.9 coulombs of charge pass through the light bulb, pass through the battery, passes through the switch per unit time. And when we talk about a unit time, we're actually talking about a second, okay? Now, this is the flow of charge, okay? And that's our total current in the circuit, which is actually the current that passes through the light bulb as well as the battery, which is the source of energy, right? What if then we close the other switch so that the second light bulb becomes part of the circuit? Let's see how that affects the magnitude of current, okay? If we close that switch, you can see now the current is doubled, okay? What does that mean? It means now more charges pass through a point for every second, okay? Now, our initial reading was 0.9 amperes. Now it's 1.8, which is actually double, okay? As you can see, now both light bulbs, let's call the first one light bulb 1, and then the second one light bulb 2. Now, if both of them are connected in parallel, what has happened here? The amount of current that is passing through the battery, or the main current, which is our total current, has doubled because we've added another resistor in parallel. That's the main idea, okay? So if we go back to our slide, the question that we asked ourselves, how do resistors in parallel affect the flow of charge? And what is this flow of charge, okay? In not so many ways, this flow of charge is actually the current in the circuit, okay? This is current in the circuit. Now, by connecting another identical resistor in parallel to light bulb 1, that has actually increased the current flow, okay? Increased actually the flow of charge, okay? Increased, this results in increased flow of charge, okay? So this flow of charge, we've agreed that it's current. In other words, we are saying that connecting more resistors in parallel actually increases the current in the circuit, because we noticed that there's increased flow of charge by adding another identical resistor in series, in parallel rather, okay? So the observation is that when resistors are connected in parallel, the opposition to the flow of charge is decreased. What is this opposition to the flow of charge? So what we have underlined, actually, the term that describes that is actually resistance, okay? So what has happened here, by adding another resistor, identical resistor in parallel, it has increased, you know, the amount of charge that passes through a point, which is the current. But what has that done to the opposition? It means the opposition has become less. So in short, we are saying that adding more resistors increases the current while decreasing the resistance in the parallel circuit. All right, okay. So that's as far as, you know, the first segment and how exactly flow of charge is affected by, you know, having multiple resistors that are actually connected in parallel. So when we come back, we'll explore more about potential difference in current in as far as, you know, a parallel circuit is concerned. Let's take a short breather for now.